Hello everyone, we are starting a free open lecture in our Discord. All our lectures are held weekly without interruptions. If you, the viewer, want to ask questions online and receive answers, join our lectures. You can find the link to Discord in our Telegram channel. To find out the schedule for the lectures, join our Telegram channel. Today we will explore the structures of dynamic programming through classic problems such as the Grasshopper, Turtle, and if time permits, also the pet store. In our exploration, we will thoroughly examine and consider all possible versions, or as one might say, the various gradations of difficulty that can be encountered in these types of problems. To begin our journey, we will start with the intriguing example of the Grasshopper, which serves as an excellent starting point for our discussion. So, what is the essence of the problem? Well, the Grasshopper is on a pole, and it can jump based on certain conditions. I will clarify further depending on the version of the Grasshopper. And it is absolutely essential to find the number of ways, in a multitude of various different ways, the Grasshopper can get from the first pole to the zero pole. In the very first classic and original version, the Grasshopper character is able to leap or jump either one or two poles or steps forward in the game. So, he is located somewhere, let's say on the zero pole, and he can jump either to the first or to the second. To ensure that the Grasshopper can reach the desired pole in the greatest number of possible ways, it is essential for it to successfully navigate to each of the poles listed within the array. This involves carefully planning its path and considering all potential routes that could lead to the. So, we have some pole here, and we need to carefully and in the most optimal way possible calculate how to jump to it and how to jump further from it in order to succeed. Well, let's just say that for some specific pole x, this is indeed the number of different ways. The Grasshopper can actually reach that particular position, indeed actually. This number, if we build a dynamic programming approach forward, will be transferred onwards to the i+1 and i+2 poles, such as in the process of dynamic programming, which is crucial, TFSP. Here, a classic combinatorial approach functions efficiently and effectively, indeed meaning that if we can reach the current position in this number of ways, we can also pass that number forward, because we can reach both the position i+1 and i+2 in the same number of ways.
Want to become a great programmer? Subscribe to our Telegram channel.
Accordingly, if this is a database backup, in this particular scenario, we will have a recurrent formula where we will jump to the current pole, specifically from the first and from the second, as a result. In other words, the variable x will be carefully and meticulously constructed from the total sum of all the possible ways to make a jump. To reach I2, I1. This will be our recurrent formula. I2 is indeed equal to I1 plus I2. The task, as you can comprehend, is to find the number of ways to reach this column in various possible ways. The starting value A0v is equal to 1. We are at this column. At the start of CD main, this already gives us one way. From here, main will start counting all. Thus, the optimal answers will be stored in an array where each cell will contain the number of ways to reach the given column. This array is constructed to efficiently store and retrieve solutions. Each cell is designed to hold the computed number of possible ways to reach the specified column. Well, yes, the first elements may lead to an out-of-bounds array access, so we prefer the first two elements accordingly. It will look something like this in pseudocode TFSP in Python or in pulses, meaning we initialize our little array with all values as fractions except for the first position, which will be equal to 1. Then we refer to dp for the previous values at I1 or I2. This is how I iterated through it. So the step can be either 1 or 2. The tournament is included. For dpj, specifically in our implementation, we will also have an array initially filled to 0. That is, it will first be filled with 1, its height will be calm in order to pulse everything, and we will use the current value. So for some reason there's a minus here. A plus should be everywhere. We add to I plus the first column and to I plus the second, we will send our values to this columns. And so we will go all the way to the end. Yes, here we also generate an array, and we step forward, either 1 or 2 columns ahead. Well, the answer will be stored in the nth column. We need to jump to n. Are there any questions about the classic Grasshopper? Yes, if anyone noticed, the classic Grasshopper is purely Fibonacci by the formula, by the very process. But this is just the classic Grasshopper. There will be a gradual complication ahead. That is, for example, if we can already jump forward by 1, 2, or more columns, then our regulatory formula will be supplemented accordingly. In essence, now we will need to look back at the I3 column of TFSP as we proceed further, and accordingly, our code will be somewhat updated to reflect these new requirements. For instance, in this case, we will iterate back from I1 to I3 inclusive. Furthermore, for the dynamics of the Grasshopper, we will use the current value for 3 consecutive columns from I plus 1 to I plus 3. Well, yes, we also iterate just moving forward, and so it will continue to develop in a manner that is consistent with its inherent and natural nature, this repetitive and recurring formula, until we have access to some set of initial steps from one deck, and accordingly, we will have a recurrent formula that also goes forward, or rather even further back if DP is backward. Yes, we will look further and further back, closer and closer to the beginning of the array, that is, from I1 to IK. At the same time, we will be able to pulse forward from I1 to IK. The only thing that will change for now is the value in this boundary form. Earlier it was 3, 4, but now it is simply k plus 1. Therefore, we check to ensure that we do not go out of the array's bounds. If this is dp backward, then at the beginning. If it is dp forward, then at the end, we need to ensure we do not go anywhere. For dp forward, we will look from I plus 1 to I plus k of this element. The complexity of such a solution will be n times k, roughly speaking, squared. In the scenario where the value of the variable k is such that it surpasses the variable n, then the result will be purely n squared, TFSP. The first 2 vertices of the Grasshopper were essentially beyond the line with a small constant. So, how can we furthermore modify the options in order to move along these columns in a way that is efficient and effectively let the Grasshopper be able to jump forward any length, but one must be a multiple of some code. Accordingly, the main feature of such a situation is that the nth Grasshopper and the nth column must indeed be divisible by k. Otherwise, we simply won't be able to jump there, essentially. Accordingly, the recurrent form will be modified to take these adjustments into account. That is, we will now refer back to ik and I2k, and so on, back to the very beginning of the array, tracing each step meticulously. Accordingly, yes, here in this section, we will also move by g, not through the consecutive elements, but rather in a more strategic manner. First of all, let's discover exactly what happens if we divide m by k, where k is now a divisor. These will be the available procedures or steps, such as multiplied by k forward or backward. In other words, that is, we go through the process of iterating g from 1 to q plus 1 and carefully multiply g by k. This way, we can refer back to steps that are multiples of k, step by step. The same will work for dp forward. That is, we will refer to I plus 2k, I plus k, and so forth, and so on until the very end of the array in the sequence. We will also find q and will already multiply g by k as we proceed going forward. There are still some questions about what is happening here. We will gradually expand the ways to move for now, and then we will add some other conditions. TFSP, if there are any questions, please ask. In the next step, additional new conditions are added. Furthermore, we won't just be jumping back and forth, but we might also have unexpected and exciting adventures along the way. Let there be frogs on some posts, or perhaps even somewhere. If the grasshopper unexpectedly and swiftly lands on a post with a frog, the frog eats it. That's it. He has certainly arrived, so to speak, at his destination. He won't be going anywhere from here. And accordingly, if we are specifically using dynamic programming backward, we will simply skip over the posts with frogs when going back, meaning that we won't refer to that post since we were eaten there and can't retrieve anything but 0 from it. Therefore, there will be a check to see if a frog is on the current post. If it is present, we move on to the next post. Otherwise, we will pass along ways of reaching it, depending upon how exactly we'll move here. In this bubble diagram, I have already shown several options for jumping both forward and also backward. For DPWG forward by way of example, the complexity involved becomes higher. Yes, indeed, for DPWG moving forwards, the complexity does become higher because unlike before, where skipped posts immediately occurred, now should one jump onto some nonsense situation arises, then checking how such current posting might still serve useful purposes towards further movement ensues instead, thus ensuring I plus J doesn't land atop any froggy. Postings remains essential, and only in this case we will be passing values there as well as checking for presence, but let's say in the array this takes some time, although here we can actually return it in constant time. However, if it is still an array and for some reason cannot be reformatted, then it will result in a cubic complexity. Even such tricks are not taken into account here. We immediately check if there is a frog in the cell or not. If there isn't, we proceed. If there is, we skip it. In the worst case, we will have a quadratic complexity. Then we can explore other options like using a set. No, please kindly set skips if possible. There is definitely a hash under the hood of this system. However, it will always check for presence in itself in constant time. It's quite similar to a dictionary structure, where everything is based on hash tables, and checking for the presence of an element, well, almost constant time indeed. If perhaps this particular element has an unusually long name, then it will add some sort of additional constant factor based on its length, specifically speaking. In my opinion, and I must emphasize it's just my own view, there should also be something akin to what we call a map within Python's framework, but honestly, I don't remember precisely if that's available at present moment. However, nevertheless, operations would still occur within that same realm of being executed in consistent timing. Python is written in C++, so it's unlikely to be inferior. So let's continue. Are there any other questions, just to clarify? If you have any additional or further questions, by the way, aside from working with this one. All right, everyone, let's continue on this journey. We have more exciting things coming up and more adventures to explore. Various types of poisonous plants that are harmful and potentially will damage our grasshopper along with the frogs and to the environment. He needs to reach the end as safely and as little battered as possible in order to succeed and successfully. The table has been updated to reflect the impact of TFSF plants on each column, showing the extent of damage caused by these facilities. And we will have this recurrent form, meaning that if we already have some damage on the current column, we look back at some previous column to achieve a total damage that is less. So we refer back to what was calculated there, add the damage from the current column, and obtain the minimum. This is our optimal option to incur as little damage as possible. Accordingly, if there happens to be a frog on this column as well, we will consider the damage as plus infinity, meaning that it is game over for the grasshopper. There's no chance. Initially, everything except the starting column will be infinite. The starting column will, by default, be 0 indicating that there is no damage here. However, if there is damage from frogs, it immediately becomes infinite. Moving on, if we have a frog, we immediately skip the current column, because if we skip it, we do not change it, and it remains infinite. If it is still possible to survive here, so to speak, we will look back at the damage, add the current one, choose the minimum, and thus we will reach the end. For dynamics.
Want to become a great programmer? Subscribe to our Telegram channel.